Good morning, everyone. So we've done processes, we've done threads, and with homework 7, we will have done both processes and threads for a parallel sorting program. After that, our next topic is going to be memory allocators. For homework 8, you're going to be building a memory allocator. So this week's lecture is going to be setting up for that. Now, the first thing that I want to talk about in order to get that to happen is some more stuff on virtual memory. So actually, it's not just homework 8 that's about memory allocators. Homework 8 is followed by challenge 2, which is going to be another memory allocator. But before we get into that, we have to talk a little bit more about page tables. So we talked about virtual memory a little bit previously. The basic idea is that every process gets its own virtual address space. And memory, as seen by the process, and memory in the system, is managed in pages. Pages are usually 4K. But it turns out that we actually sometimes can have bigger pages. Mostly we can ignore that for the purpose of this class, but it's important for completeness. But what this means is that we need a lookup table for every single active process. And this lookup table is going to need to map virtual pages to physical pages. So that raises a couple of questions. I'm going to start off by talking about the 32-bit Intel architecture, just because it's a little bit smaller numbers and therefore simpler to figure out. So with 32-bit page tables, this is talking about systems like the Intel 386, or if you went and got a Pentium 4 back in 2003. So we've got some questions that we can look at. How many potential 4K pages fit in a 32-bit address space? Now, that's a question that you should be able to answer, so go ahead and pause and think about that for a second. How many is it? So to answer this, we could just say that the address space is 4 gigabytes, and then divide that by the number of 4K pages. And the way that I want to do that is by saying that 4K is 2 to the 12. And then we can just subtract to do division. So we say 32 minus 12 is 20. So we have 2 to the 20 pages, or 1 meg. 1 meg pages, 1024 times 1024 pages. So, okay, every running process on a 32-bit system is going to need to have a map which allows it to map physical page numbers So we need to be able to map 1 million potential virtual page numbers to 1 million potential physical page numbers in every process. So how's this map structured? First thing that we need to know is how big is a page table entry. So for every mapping of a virtual page number to a physical page number, we're going to need to store one page table entry. And for that, we're going to need to keep track of so the index into this, the key that we're using in the map, is a page table number. Sorry, is a virtual page number. And that's 20 bits. So we have a 20-bit integer. But the index into a table doesn't really take up space unless we're using a hash table, and then it does, but turns out that we're not using a hash table. In fact, what we end up using is more like an array. So then in the table, we also need a physical address, or a physical page number, which is also a 20-bit number. Then we need permissions. And some other flags. Like we know for every page, we have, is it readable, is it writable, is it executable, is it copy on write, we've got some number of things that we need to store in there. And so for the, the real question is, can we fit it in 32 bits or do we need 64 bits? Let's go ahead and assume that we need 64 bits. That gives us a bunch of space for flags, it gives us a little bit of space for other information, but that means that we have to have this table mapping 20-bit numbers to 8-byte entries. So if the table is an array, that's 1 million entries, 8 bytes per entry. So that's going to be a total of 8 megabytes for a table. And we need a table for every single process. This turns out to be a problem. This is actually a really serious problem for designing the system, because the original Intel i386 came with like 2 megs of RAM. So we're talking about, even to have a single process, if we're going to run it in a mode where we have virtual memory with page tables, it's going to take more memory, and we have to keep the page table in memory, because otherwise it gets real confusing to figure out how to translate. Like reading page tables off disk to figure out what memory, we don't want to deal with it. Page tables go in memory. So we don't even have enough memory in the machine to store the mapping for one process, much less multiple processes. If we think about a more typical 386 or Intel x86 style machine, we might have, even at the end, when these 32-bit machines went out of style, you'd be talking about 2 gigs of RAM in a computer. And with 2 gigs of RAM, that's 2048 megs divided by 8. Just the page tables would fill memory if you had 256 processes. And if we take a sort of random computer, PS AUX, list all the processes on this particular computer, go ahead and count them up. I have 478 processes running on my desktop computer right now. Now, sure, OBS is a process. I probably have web browsers in the background, and you can see a terminal window and Emacs here. But getting to 478 is pretty easy. I'm not even running a full desktop environment here. So clearly we can't actually have 8 megs of just bookkeeping overhead for translating virtual memory for every single process. Let's make it even worse. Let's look at 64-bit page tables. So how many potential 4K pages? It's still 4K by default on both 32 and 64-bit Intel style systems. So if we want to have a 64-bit address space, we're going to have two to the 64 divided by 2 to the 12 is 2 to the 52, and suddenly every single process needs 2 to the 52 bytes of memory. Sorry, 252 rows, where each row is like 8 bytes. Now, none of that's going to happen. So the way this is actually implemented is a solution called multi-level page tables. There's a couple ways we could implement this. We could say that we were going to do hash tables. We can't do hash tables. And the problem with hash tables is, although they're expected amortized constant time, having them be either expected or amortized constant time isn't really good enough. When we're doing a memory access, we're trying to translate a virtual page number into a physical page number, we want it to not be mostly constant time, we want it to be actually constant time. Having trying to read a item in an array in memory and having it take linear time in the size of the virtual address space to do a lookup isn't okay. We can't have these hash tables resizing. Or we can't have a bad hash function that resulted in too many collisions. A slightly better idea would be to have a binary search tree. But at least with the initial way we're looking at this, we're talking about pretty much every memory access needs to do a translation between a physical address and a virtual address, and we don't want to be slowing down by a factor of log n. We'd like to be slowing down by nothing, but log n is a little bit too much since, we know log n is 20, and that's a pretty big factor. You have to go through 20 levels of table. So the solution that they actually came up with for 32-bit Intel systems is that we're going to split up our table into 2 levels. So we're going to have a root table that we're going to use to look up the first 10 bits. And then we're going to have a leaf table. This is the first 10 bits. Well, this gives us the page table row, the actual page table entry. And the benefit here, let me draw a bad picture. So we have our address. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bits. Then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bits. Let me make this be like a 1, make this be a 2. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's make this have a 3 in it. So this is a 32-bit memory address. And the way we do our page table lookup is we're going to use the first 10 bits as an index into an initial table. So since this is a 10-bit table, that means the table is going to have (1024) entries. And all we actually need to store in this first level table is a 20-bit memory address. We could just store a 32-bit memory address in it, which is where the next table is. So once we find the next table, we're going to use the second 10 bits to store the next table. Which is going to store our page table entry. And then, by having looked at the first 20 bits, that's sufficient to find the physical page number. And the last 12 bits of the memory address are offset within the page. Which byte among the 496 bytes is it that we're trying to access? And having two levels of page tables means that we can simply not allocate second level page tables that aren't used. So whereas with a single level page table, the minimum size for a process is something like 1 page for stack, 1 page for heap, 1 page for data, 1 page for text. So like 4 pages. And these pages aren't necessarily next to each other logically in memory, but to store the mappings for these 4 pages would take 8 meg in a single level table. In a 2-level table, we can have the stack and heap each get their own second level table because they're not next to anything else in memory. We can have data and text share a second level table because they can do that if our executable is smaller than 4k times 1024, which is the number of rows in a second level table. So if our executable is smaller than 4 meg, if the data and text section are smaller than 4 meg, we just need a single second level table. So we need for our 2-level page table, we need to have top level table is 4096 is going to be 1024 times 8 is 4096 bytes. Then we have 3 second level tables is going to be, I'm bad at math, 8192 bytes, 8k bytes is going to be 8 times 3 equals 24k bytes. And so the minimum allocation for page tables here is somewhere around 32k, and even on the old like i386 with 2 megs of RAM, allocating 32K for every process for page tables is okay. It's not great, but it's okay. Now, this gets a little bit more complicated when you have 64-bit tables. So instead of having our address broken down into 3 parts, 32 bits breaks up as a top level table 10, a second level index 10, and then a page offset 12. With a 64-bit page table, we have to come up with some way to break 64 bits up between multiple pages so that it makes sense. And it's worth thinking about that for a second. How would you do that? Pause now and think about that. Alright, now that you've paused, what they actually did, so AMD is sitting and staring at this architecture that Intel came up with, and they're trying to figure out how we're going to make it work. AMD decided we don't need 64 bits. 48 is plenty. Once they had 48, they had the next choice. So 48 minus 12. Offset is still 12 bits because the pages are still 4K. That leaves 36 bits for indexes. So they could split that up 18 and 18, in which case every table would be 200 million rows, which is a little bit too much. I mean, it could fit. We could use 200 megs of page table for every running process, and that would be possible. But we don't want to deal with it. So rather than having 2-level page tables, AMD went with 4-level page tables. So we have 9, 9, 9, 9, and then an offset of 12 for a total of 48. And I mentioned back at the beginning of class that they started off with this architecture only supporting 48 bits of physical memory address in hardware, even though they had a 64-bit field to store it in. And further, that when Intel started shipping servers that needed more physical address space than that, they didn't go to a 64-bit physical address, they went to a 57-bit physical address. And now we can see why 57 is the number that they came up with. So 5 times 9 plus 12 is 57. So that's an option if you have a really big server. How big a server do you need before this is necessary? Well, 2 to the 48 is 2 to the 10 would be K, 20 is meg, 30 is gig, so 40 is terabyte, so this is 256 terabytes. So if you have more than 256 terabytes of physical memory in a machine, then you're going to need to have you're going to need to go to 5-level page tables, and that was sort of broadly supported in Linux as of a couple years ago. So this is something that you can just enable when you're compiling your Linux kernel, and it works fine. All right, so we have another problem. The next problem that we have is that programs use virtual addresses, and so we have to actually do this translation. So with two-level page tables, if we want to do a lookup, if we want to do a memory access, so when we do an instruction that accesses a memory address, we need to translate that virtual address that the program's working in into a physical address to actually send down the memory bus. So hardware can handle this lookup. Modern processors have a MMU, which can do this translation. Intel and then AMD specified the format of the multi-level page tables, so the hardware can do the traversal of the data structure to do the map lookup. But it still takes an extra 2 or 4 memory accesses to get the data. Before we can go ahead and access memory, we first have to look up the translation from physical to from virtual to physical, and that means on a 32-bit system we have to access the top level table, we have to access the second level table, and then we can finally do the thing that we wanted to do. Which would mean that every memory access actually takes 3 memory accesses, which would mean that we are a factor of 3 slower at a lot of stuff executing code than we would be if we weren't using virtual memory. And spoiler alert, if that's how computers actually worked, we simply wouldn't use virtual memory. Someone would have shipped a machine, like Intel would have tried to do virtual memory with the Intel 386 or 486, and like Microsoft would have shipped an operating system with virtual memory turned off, and it would have sold better because it ran faster by a factor of 3. It would have run Doom at a higher frame rate, and people would have bought that instead. So this is clearly not actually what happens. So the solution here is that we have a cache. And that cache is called the TLB, or Translation Look-Aside Buffer. And it stores about 1,500 translations of a virtual page number to a physical page number. And this is in the processor, real close to the registers. So TLB lookups are super fast, and so we only have to actually do the multi-level page table traversal if we haven't seen this page recently. And for most accesses that we're doing, we're accessing in sequential order, so we don't have to worry about not having seen the page recently, because we do a memory access, maybe we haven't seen the page, we have to go do the lookup, and we get it into the translation buffer, but then we access the next byte in memory, and it's right there in the translation buffer, because we're on the same page. So let me do a quick example here. Consider the following code. So we're going to have an in pointer, x's, that points to an array of length 2 pages. And then we're going to say for So 2 pages of stuff for an array of integers is going to be, size of int is 4. So if we want 2 pages of integers, we need 2048 integers. Every int is 4. So 1024 ints is a page, 204 ints is 2 pages. So if we go through this loop, we're going to be accessing these 2 pages of integers sequentially. Now, let's consider without TLB with the 4-level table. So 2048 integer accesses. This load here happens 2048 times. Now, we're going to do that once to actually load the integer, but then for every time we access the integer, we're also going to have to do the TLB lookup. So that's going to require a traversal of a 4-level table. So that's going to take about 10K memory accesses. But when we add in the TLB, we have 2048 times 1 for the actual memory accesses that we care about, and then plus 2 times 4, because every time we attempt to access a page of memory where we don't have a translation, we have to go do the 4-level lookup. And so when we get to the first page, so on index 0, we're going to have to do a 4 memory access lookup. And then when we go to index 1, that translation will already be in the translation look-aside buffer because we looked it up for index 0. Similarly, when we get to index 1024, that's on the second page. And so we don't have that index, so we have to do a lookup. So a second time, we end up having to do the lookup. But with 2 additional lookups, it would be 2K lookups without virtual memory. It's still 2K lookups with virtual memory, because the extra 8 lookups are not significant against 2048. So, at least for sequential memory accesses, having this TLB solves the problem. If we're doing really sort of huge hash tables or something, where we are doing sort of random-ish access to more than 1,500 pages of memory, we can get into situations where virtual memory slows us down a little bit, but probably the solution to that is don't do that, and you won't have the problem. And that's frequently the solution, is that we can come up with some data structure that will be a little bit better. For very large collections of data, you might want to consider something like a B tree instead of a hash table, just because it has better locality of reference, even though the asymptotic complexity sounds a little worse. All right, while we're talking about this stuff, I want to talk a little bit about context switches. So when we are running along, executing code in a process, sometimes the operating system has set up a timer interrupt that will rerun the scheduler and see if we need to run another process on the same CPU core. So we're going to have a 1-core processor. Works the same on a multi-core processor, it's just a little bit more complicated. We have 2 processes, and both of them have computations to do. They have work. So the way we handle that is that the operating system is going to preemptively schedule them, and So every, I don't know, 4 milliseconds or something, this timer interrupt happens and checks to see whether we need to switch from one process to the other one. And if both of them have work to do, then we'll just go ahead and switch back and forth every 4 milliseconds. So the way this works is, if we actually want to switch processes, the hardware interrupt is going to occur. And this is going to jump us immediately to kernel interrupt code. And in the process of getting to that handler, one of the things that happens is we're going to save off the current process state. That includes all of the registers, and stuff that we're saving just gets shoved onto the current process's stack, where the stack pointer is pointing. Generally, we have space to put stuff there, and so that's what happens. Now, because we're getting interrupted by this interrupt timer, we're going to assume that the kernel wants to schedule a new process. So we're going to have the kernel pick a new process to run. And here is where the switch actually occurs. We're going to go from saying that we're using the page tables for the old process, and instead we're just going to start using the page tables for the new process. On an Intel processor, this happens, I think, in a register called CR3, which is a special register that just points to the page table, and isn't something that you can access outside of the kernel. So we don't have to worry about it in normal code, but there is a register that points at the page table that then the MMU can use to do page table translations. But once we point to the new page table, now all we need to do is do a system call return. So in the return process, and so we're going to restore the saved registers in other state from the stack, but because we switched page tables, the stack is now the new process's stack, not the old process's stack. We may have had to do some trickery to store the stack pointer somewhere else. That happens, as is necessary. And then we just return from that interrupt handler, and we end up returning to the new process. Now, this is a reasonably quick operation. And that is, we lose all our TLB entries because we are looking at a new page table. All the stuff that we cached is now no longer valid. So in at least the way this used to work, we have to just, as part of this process, when we switch from the old page tables to the new page tables, we invalidate the TLB. And so now for a little while, every single memory access, the next several, if we're going to be doing sort of randomish access, are all going to be TLB misses. And so this is one of another benefit to threads over processes. The context switch operation between threads is actually reasonably similar. We just don't have to switch page tables. All we're doing is switching stack pointer. So that's an important part of this story. So So that's what I want to say about this mostly for the moment. Oh, a couple more reasons we might context switch. So we definitely context switch from the timer interrupt, but when a processor thread blocks for some reason, that tends to put it in a non-runnable state, and so the kernel is going to go ahead and immediately reschedule. For example, IO, IPC, and blocking for something like reading from disk tends to be faster than sort of busy waiting because we have the opportunity to do something else during that time, but it does mean that we have to do this context switch. So that's that story, and I'll be back in a moment with some more stuff.